Hi everyone, my name is Noatira binti Muhammad Rozlan and I have 4 members with me. I have Ahmad Faris bin Ramli, Intan Dayana binti Nordin, Muhammad Nashafiq bin Abdul Ghani and also Muhammad Arif Rashdan bin Abdul Rahman. So today I would like to talk about the introduction and principles of prestressed and precast concrete structures. What is prestressed concrete? Internal stress are induced to counteract external stress. Is creation stress in structure for improving the strength under various surface conditions. Is also that compressive stresses induced by the high strength steel tendered in the concrete member before loads are applied. This will balance the stress imposed in the member during the service. Next slide is concept and principles of prestressed concrete. So the concept is the metal bands were tightened under tensile stress, which create compression between the stuff, allowing them to resist internal liquid pressure. The principle. Prestressed concrete works on the principle that compressive stress caused in a concrete member by high strength steel tendons before loads are applied offset the tensile stresses exerted in the member during operations. Compression force is applied to the reinforced concrete sections, and the effect of prestressing is to reduce tensile strength to the point the tensile stress is below the cracking stress and the concrete does not crack. Next one is, as you can see in the slide, number 1, when we apply load on the concrete member, the member bends like this, and from this you can see compression develops on top portions and tension develops at bottom portion. Due to this elongation at bottom, concrete get cracks. And then number 3, as you can see the red arrow, this is why we add some steel bars at the bottom section and stretch so that it can resist most of the tension and save concrete from cracking. This is space where we call it as prestress. And the number 4, the tendons are stretched along the axis and concrete is poured later. When the tendons are released, the compression is generated at the bottom, which tries to counterbalance the compression due to the loading at the top part of the beam. And the number 5, the output force along the length of the beam counteracts the service load applied to the member. And the number 6, prestressing removes design limitations of conventional concrete and permits the buildings of roof, floor, bridges, and walls with longer unsupported spans.
Okay, next this is link short video from the YouTube. In this video, it is mentioned that pre-stress can be in 2 ways, which is pre-tensioning and post-tensioning.
Pre-stressing can be done in 2 ways. One is pre-tensioning and other is post-tensioning. Let us discuss about pre-tensioning first. In pre-tensioning, the steel is stretched before the concrete is placed. High-strength steel tendons are placed between two ends and stretched to 70 to 80% of their ultimate strength. Later, the concrete is poured around the tendons and allowed to cure. Once the concrete reaches the required strength, the stretching forces are released. When highly stressed steel attempts to contract, the concrete gets compressed. Then the concrete will be in a permanent state of maintaining pre-stressed strength. Mostly the pre-tensioning concrete elements are precast in a factory and must be transported to the construction site. In place of tendons, wire strands or cables, high tensile steel bars can also be used for tensioning. Examples of pre-tensioning concrete precast products are foundation pile, railway sleepers, electrical or lighting pole, floor slab, beam, pipe, partition wall, etc. Post-tensioning. In post-tensioning, the steel is stretched after the concrete hardens. Unlike pre-tensioning work, post-tensioning is usually carried out at project site. In case of post-tensioning, a sleeve or duct is placed into the concrete structure. Concrete is casted and allowed to cure. When the concrete reaches its required strength, the tendons are stretched and locked with anchors. The excess ends of tendons are then cut away and the duct will be grouted and covered with concrete for rust prevention. Examples of post-tensioning are roads, bridges, railways, tunnels, dams, containment tanks, reservoirs, underground constructions, foundations, buildings, industrial facilities, air and sea ports, special structures or any form of pre-stressed concrete structures, etc.
Okay, first pre-tensioning. In pre-tensioning, steel is stretched before the concrete is placed. High-strength steel tenders are placed between two and stretched. The concrete is poured around the tenders and allowed to cure. When the concrete reaches the required strength, the stretching force are released. When highly stressed steel contract, the concrete compressed, then the concrete will be in permanent state maintaining pre-stress strength. Precast in the factory and transported to construction site. Wire strength or cable high tensile stick can be used. The example we can use pre-tensioning is on foundation pipe, railway sleeper, electrical or lighting pole, floor slab, beam and pipe. Next, for post-tensioning, steel is stretched after the concrete hardens, usually carried out at a project site. Sling or die is placed into the concrete structure. Concrete is casted and cured. When the concrete reaches its required strength, the tendons are straight and locked with anchors. The excess end of tendons are cut away and the duct will be covered with concrete. The example that we can use post-tensioning is on high road, bridge and railway road.
Next, we continue with justification of precast concrete is preferable compared to cast in situ concrete. There are several justifications on why precast concrete is preferred compared to conventional in situ construction method. In a construction project, time, quality, and cost are the main factors that need to be considered in a project. As you can see, the top three of the justification advantages are more on pre-stressed concrete. As the pre-stressed concrete take less time, hence the speed of construction will increase. Next, pre-stressed concrete is made in a controlled production in the factory, where the weather conditions have zero effect during the production. Therefore, the curing process is controlled and early strength can be achieved compared to cast in situ concrete. The production in the factory can produce similar type of components in fast rate. Also, in the factory, the strength test will be conducted so that the test does not require to do on site. Moreover, material wastage can be controlled as the pre-stressed concrete can be adjusted by renovate internally. And last but not least, it can save space and can be ordered directly from the factory when required.
How precast concrete construction can contribute towards reducing carbon dioxide and global warming issue. Transportation contribute 12% carbon emissions of cast in situ, while it represents 18% of precast. The larger transport emissions of precast concrete are mainly due to the process to transport precast elements from precast yard to the construction site. Although precast concrete has higher transportation emissions, the overall carbon emissions of precast concrete are much lower than those of cast in situ concrete. It was discovered that 1 meter cube cast in situ concrete emits 770 kilogram carbon dioxide, while precast emits just 692 kilogram of carbon dioxide, which is around 10% less than cast in situ concrete according to Dong et al. 2015. Uh, According to Jailon et al. 2009, it is stated that the use of precasting method will result in a 52% waste reduction and a 70% reduction in timber formwork. Steel formwork can be reused up to 100 or 200 times, while timber formwork can only be reused less than 10 times. Steel formwork is a recyclable material with high recycling content of over 90%, which can also reduce the carbon emissions of steel formwork according to Poon et al. 2004. Based on the previous study that conducted by Dong, Jailon, Chun Poon in 2015, uh, about the comparing carbon emissions of precast and cast in situ construction methods that based on a private residential building in Hong Kong. This paper highlights about the adoption of precast concrete that can reduce the carbon emissions. The carbon emission of 1 meter cube cast in situ concrete is 692 kilogram carbon dioxide. For 1 meter cube concrete, precasting can lead to 10% reduction of carbon emissions, and the adoption of precast facade can reduce 2.1 kilogram of carbon dioxide per meter square. Okay, this is the statistic that this research provide. So as we can see over here, it is clear that the use of precast in construction can reduce the carbon emissions. So uh, based on this research also, it is highly recommended that we need to adopt precast concrete in building construction. The building industry should consider the carbon reduction as a benefit to implement precast concrete, which further can be incorporated into the building assessment schemes. Uh, the government should provide more incentives that can encourage adoption of precast concrete in private sector. While this study is based in Hong Kong, the research outcomes can be potentially applied in our country of building projects that adopt precast concrete, in particular for high-rise residential buildings.
Precasting can lead to 10% carbon reduction for 1 cubic meter concrete. Steel formwork for precasting perform better than timber formwork used in cast in situ concrete. Adopting more precast concrete can lead to less carbon emission. Global warming potential (GWP) associated with manufacturing cement is approximately 3 times greater than the GWP associated with utilizing precast or cast-in-place concrete construction method. From a study, it show in this graph the result of carbon dioxide emission from manufacturing, cast-in-place and precast. Here we can see the manufacturing industry lead to more carbon dioxide emission rather than precast and cast-in-place concrete. Global warming is highly caused by the emission of carbon dioxide by industry. When we use precast concrete, the amount of waste of cement can be reduced, so the manufacturing of cement can be utilized optimally, leading to less production of cement from the factory. Although precast concrete might not directly contribute to reduce global warming, it at least a measure to reduce the manufacturing of cement in the industry.